celebrate Mike's career. So I'd like to begin with a slide that maybe I've used too often, but I'll try to do it one more time and then perhaps tell you why I shouldn't. So, so motivation for a lot of the work on classifying smooth core manifolds is the classification of complex surfaces. So typically, one classified, well, this picture is called the geography of complex surfaces, and what you see is a graph with the horizontal axis denoting the holomorphic Euler characteristic of a complex surface. So for topologists, that's just the signature plus the Euler characteristic divided by 4, and I was careful here to tell you that the signature is the difference between the dimensions of the positive and negative eigenspaces of the intersection form on the second homology. And the vertical axis is square of the first Chern class, which is 3 times the signature plus twice the Euler characteristic. So these are both given by topological quantities. And two very important lines that run through this picture are the Bogomolov-Miyoka-Yau line, which is C1 squared equals 9 times the holomorphic Euler characteristic. And because I said this is the geography of simply connected minimal complex surfaces, the only complex surface that's simply connected that lies on that line is CP2. There are lots of other surfaces that lie on this line, but they're all ball quotients, so they won't be simply connected. The other important line, the one here on the bottom, is called the Noether line. It's given by C1 squared is 2 chi minus 6. And also important, is the horizontal axis itself, C1 squared equals 0, where elliptic surfaces live. So I'll talk more about elliptic surfaces in a minute, but the simplest are denoted E1, E2, and so on. And they live exactly at the points 1, 0, 2, 0, and so on. E1, though, I needed to note, is not minimal. That's actually CP2 connected some 9 CP2 bars. So the elliptic surfaces live along the horizontal axis. There's a classification of minimal complex surfaces, simply connected complex surfaces, and it says that there are 3 kinds. There's the elliptic surfaces, the ones that lie along C1 squared equals 0. There are the rational surfaces, so these are topologically CP2 blown up, so CP2 connected some a bunch of CP2 bars, or S2 cross S2, and the rest are called general type. And the fact about general type, minimal surfaces of general type, is they must live in between the Noether line and the Bogomolov-Miyoka-Yau line. And now there's where S2 cross S2 lives, and these dots that I just amplified are where recent work, well, some recent, has shown that there are exotic surfaces. So there are surfaces of general type which actually live along this line. This is the line B plus equals 1, where the rational surfaces live. So I'm happy to be able to mention Mike's work. And it tells us that if we're thinking about smooth, simply connected core manifolds, when B plus is 1, then the classification is quite simple up to homeomorphism. Namely, those with odd intersection form are CP2 connected some a bunch of CP2 bars, and with even intersection form, just S2 cross S2. So that means that the homeomorphism type of a simply connected smooth core manifold with B plus equals 1 is determined by its type, namely its evenness or oddness of its intersection form, and the rank of its second homology. And although this doesn't quite fit, this reminds me of one of my favorite quotes, and it's due to Mike, about core manifolds. So right after he won the Fields Medal here in '86, he was interviewed. Was it the New York Times? He was interviewed and asked, why did he win the Fields Medal? And the answer was, well, I won the Fields Medal for proving that certain manifolds exist, and Simon Donaldson won it for proving that they don't. I don't think the correspondent actually understood the subtlety of the comment, but it was funny. Okay, so next let me say a word about elliptic surfaces. So the most basic elliptic surface is one I'll call E1, and it's CP2 blown up 9 times, so connected sum with 9 CP2 bars. So an elliptic surface is a complex surface that fibers over CP1 with generic fiber, a torus, so an elliptic curve. Of course, it can have singular fibers. This isn't a fiber bundle. And one way you can see that E1 has such an elliptic fibration is to look at CP2 and take a pair of smooth cubic curves. They'll intersect in 9 points. So you take a pair of them, they'll give you a pencil, and but that pencil will have 9 base points, 9 points where all the curves come together. And now if you blow up, you'll separate them all, and you get a fibration. So that's how you get E1. And the way to form bigger elliptic surfaces is by forming a fiber sum. So fiber sum just means remove a neighborhood of a generic torus. So that's a D2 cross T2. You'll be left with a manifold with a T3 boundary, and now glue them together. But glue them together in such a way that you preserve the fibration, and that gives you En. So En has Euler characteristic 12n, and B plus is 2n minus 1. So in this talk, I'm going to restrict to B plus equals 1. So we're only going to be considering among these surfaces E1. And probably the most important operation that you can perform on an elliptic surface is, at least from a topologist's point of view, is log transform. And this is really just, in some sense, S1 cross Dane surgery. So you remove a neighborhood of a torus, of a generic fiber, and reglue it. And when you do that, it now obtains the torus in the middle of your solid torus now can be multiply covered by fibers around the outside. And the way you can measure that multiplicity is by restricting the projection of the fibration to the boundary of a normal disk. So that gives you a map from the circle to the circle, and it just counts the number of times a regular fiber runs through it. And so that multiplicity is called the multiplicity, its degree is called the multiplicity of the log transform. And I point out here that if you do S1 cross P over Q Dane surgery, then it has multiplicity P. And in fact, when you have a simply connected elliptic surface, the result of the diffeomorphism of this operation only depends on the multiplicity of the log transform. So let me say a word about exotic complex surfaces. So first of all, there's the Dolgachev surfaces. So these were surfaces that were discovered by Igor Dolgachev in response to a conjecture of severity from the beginning of the 20th century, or the end of the 19th century. And this conjecture was that a complex surface with irregularity 0 and PG 0 should be rational. So understandable to us is to say that if a surface is simply connected and B plus equals 1, then Severi's conjecture is that it needs to be a rational surface. And if you take this complex surface E1 and do a single log transform, it's not too difficult to see that what you get back is E1 again. And this is true even complex analytically, where there's there's this Castelnuovo criterion, which tells you when you have a rational surface, and if you do one log transform, that criterion is still satisfied. So, but Dolgachev proved that if you do two log transforms, then your surface is elliptic, B plus equals 1. It's still homeomorphic to E1. But it's no longer birational to it. So it's not a rational surface. And in 1985, Donaldson proved that the simplest of these Dolgachev surfaces is actually not diffeomorphic to E1. So this was the first example of closed four manifolds that were homeomorphic but not diffeomorphic. And a counterexample to the smooth H-cobordism theorem. And then afterwards, Bob Freedman and John Morgan proved that these Dolgachev surfaces were classified up to diffeomorphism by the pair, by the multiplicities of the log transforms that you use to construct them. And so these first examples were examples where B minus equals 9. In other words, CP2 connected some 9 CP2 bars. So the negative part of the intersection form is 9, is rank 9. Rebecca Barlow constructed a surface which actually I don't have a good topological way to describe, but the Barlow surface is homeomorphic to CP2 blown up 8 times and a surface of general type, so not rational. So this was an even better counterexample to the Severi conjecture. And Dieter Kochik showed, I guess in his thesis in 1989, that it's not diffeomorphic to CP2 blown up 8 times. So in order to tell you how you can go about detecting the fact that things aren't diffeomorphic, let me say a word or two about Seiberg-Witten invariance. So if you have a simply connected smooth four manifold and B plus is bigger than or equal to 1, then the Seiberg-Witten invariant is a diffeomorphism invariant that you can think of as an element of the integral group ring on the second homology. So it's a Laurent polynomial whose variables are elements in homology. And and written multiplicatively. So, and furthermore, only characteristic homology classes could have non-zero coefficients in this Laurent polynomial. So, by characteristic, I mean that if you take the Poincare dual and reduce mod 2, you get W2. And so here are 2 examples. So the Seiberg-Witten invariant of E2, which is the K3 surface, is 1. So this means that only 0 has a non-trivial coefficient. And that coefficient is 1, because when I write 0 multiplicatively, it becomes 1. And, no, how that happened. Never did understand. Anyway, E3, which is one more fiber sum, has Seiberg-Witten invariant T minus T inverse, where T is the element in the group ring corresponding to a fiber of the elliptic fibration. And here are some basic facts about Seiberg-Witten invariance. First of all, if you have if your manifold has a metric of positive scalar curvature, then the Seiberg-Witten invariant vanishes. So that means that all these examples that or not all of them, but most of the examples I mentioned, the standard examples with B plus equals 1, have trivial Seiberg-Witten invariant. So CP2 blown up a bunch of times has Seiberg-Witten invariant 0. S2 cross S2 has Seiberg-Witten invariant 0. And so this gives us an easy means to tell if we have constructed a manifold that's not diffeomorphic to one. And another important fact is the adjunction inequality, which tells you that if you have a class, homology class, and its coefficient in this Seiberg-Witten polynomial is non-trivial, then it satisfies an inequality. Namely, any time you have an embedded surface of non-negative square and positive genus, that it satisfies the inequality 2g minus 2 is greater than or equal to its own square plus the absolute value of its intersection number with this class. So you should compare this with the adjunction formula in complex surface theory, where you actually get an equality if K is the canonical class of your surface and sigma is representing a complex curve. And one last fact here for Taylor surfaces due to Witten and more generally for symplectic manifolds due to Kautz, if B plus is bigger than 1, then the Seiberg-Witten invariant is non-zero. In fact, the canonical class has to have coefficient plus or minus 1. And so here comes the fine print. But somehow the fine print affects us because I'm going to be talking about manifolds with B plus equals 1. And there are complications that come from the fact that when B plus equals 1, you can have reducible solutions to the Seiberg-Witten equations that occur in one-parameter families of metrics. And in fact, you get invariants. There are invariants that I prefer not to talk about, but could, called Seiberg-Witten plus or minus. And in fact, these actually determine the Seiberg-Witten invariant. And so, like all fine print, I try to get rid of it quickly. Here's a log transform formula. So in a second, I'll tell you where it comes from. But if you take a manifold that has a torus, an essential torus of self-intersection 0, so this manifold X, and you do a log transform of multiplicity P, you've got a manifold that I've denoted X sub P on the screen, and its Seiberg-Witten invariant is the product of the old one times this polynomial in T, where T is representing the multiple fiber. So remember, the multiple fiber is the core of this torus that you cut out and twisted and put back. So P times it will be the generic fiber. And so T in that formula is P of what you had before. So, and in fact, when you have B plus equals 1, this formula still works for these invariant Seiberg-Witten plus or minus. And you can use them to compute the Seiberg-Witten invariant. So here's an example. Suppose you take manifold E1 and do order 2 and order 3, or multiplicity 2 and multiplicity 3 log transforms. Then you get the Dolgachev surface that Simon Donaldson's theorem alluded to. And its Seiberg-Witten invariant turns out to be T inverse minus T, where T is 1/6 of the generic fiber. And, well, it's not 0. And the Seiberg-Witten invariant E1 is 0. And so this calculation then proves Simon's theorem. Okay, so here is another way that you can change the Seiberg-Witten invariant of the manifold, and therefore its smooth structure. So instead of, if you have a torus embedded in a manifold of self-intersection 0 and homologically non-trivial, then what surgery on the torus, or in other words, log transform does, is simplest example of this is when you take S1 times the complement of a knot in S3. So that's a homology torus. So if you remove the neighborhood of a torus, this square zero torus from your manifold, and now glue back S1 times the complement of the knot in such a way that the longitude of the knot is identified with, what you had, this boundary D2, then you don't change the homology of the manifold at all. And in fact, your intersection form will be the same as the original intersection form. And if you start with a simply connected manifold, and if the complement of your torus is simply connected, then in fact the manifold that results from this process will again be simply connected. So that means it'll be homeomorphic to the original manifold. And a theorem that I proved with Ron-Stern is that this process changes the Seiberg-Witten invariant by multiplying by the Alexander polynomial of the knot use. And again, this is true for B plus bigger than 1, but it works for Seiberg-Witten plus or minus when B plus equals 1. And from that, you can compute the Seiberg-Witten invariant, even in case B plus equals 1. So for example, if you have an N twist knot, then it's Seiberg-Witten invariant E1 with knot surgery done on it with respect to that knot is N times T inverse minus T. So this gives you a family, another family, aside from the Dolgachev family, of manifolds which are all homeomorphic to E1, and no two of them are diffeomorphic. And in fact, at most, one of them can have a symplectic structure because Taubes' theorem says that the coefficient of the canonical class must be plus or minus 1. Okay. One more technique, and then we can come to more serious constructions of manifolds. So I'd like to talk for a second about what does it mean to blow down a two-sphere in a four-manifold. So suppose you have an embedded two-sphere whose self-intersection is -1. Then its neighborhood is just the neighborhood. It's just CP2 bar, namely CP2 with the opposite orientation, minus a ball. So its boundary is a three-sphere, and you can trade its tubular neighborhood for a four-ball to get a new manifold X bar. And what has happened is you've gotten rid of a class of self-intersection -1. So that means you've lowered B minus by 1 by doing this. And in fact, there's a formula for the Seiberg-Witten invariant that says that the Seiberg-Witten invariant of X, which is the blown up manifold, is the Seiberg-Witten invariant of X bar times epsilon plus epsilon inverse, where epsilon is represented by the class of this two-sphere of self-intersection -1. So here's another way to read this formula. If you take a characteristic homology class in the blown down manifold, then it will have lifts in the blown up manifold X, namely that class plus or minus the exceptional curve E, which is representing epsilon. And this formula is saying that the coefficients in the polynomials, both above and below, are the same. Okay, so here's another kind of blowdown you can do. Suppose instead of having a -1 sphere in your four-manifold, you have a sphere of self-intersection -4. So a sphere of self-intersection -4 is the complement of RP2 and CP2 bar. And the way you can blow it down is by throwing it away and replacing it with the neighborhood of RP2 and CP2. That gets the orientation straight. RP2 is a rational homology ball with pi1 equal to Z2. So once again, by doing this, you lower B minus by 1 without changing the rational homology. Sorry, that's impossible. minus by 1. Okay, so here's what you have in general. So suppose you have a string of spheres, each intersecting the next. And suppose you have p minus 1 of them, and all of them have self-intersection minus 2. So you've got p minus 2 spheres of self-intersection minus 2, and then at the front of the parade there's a sphere of self-intersection minus p plus 2. So this is a configuration of two spheres I'll call C sub p, and its boundary is the lens space, Lp squared 1 minus p, which also bounds the rational homology ball. Call it Bp, and it's a rational homology ball with pi 1 equal to Zp. And so what rational blowdown means is you should remove this configuration and replace it with the rational homology ball. You get a new manifold, and B minus will be lowered by P minus 1, because you're getting rid of P minus 1 spheres of self-intersection negative. So here's a picture. So X star is the complement of your configuration, and you're replacing it with BP. And if, just like in the blow-up formula, if you have a characteristic homology class in X bar, then you can find a lift up in X so that when you take their Poincare duals, those cohomology classes agree on X star. And the theorem Ron and I proved is that the coefficients in the corresponding Seiberg-Witten polynomials are exactly the same. Okay, so why should anybody be interested in this? So here's one example. Suppose you have an elliptic surface, say En, and a nodal fiber. So a nodal fiber just means you have one of the torus fibers has a non-separating circle that's been shrunk to a point. Then you can blow up at the double point. And what happens is your sphere of self-intersection 0 with the double point becomes an embedded 2 sphere of self-intersection minus 4. In fact, it's representing the homology class F minus 2E1. And the red curve is the exceptional curve that blowing up introduces. So now you have a minus 4 sphere. You can blow it down. And in fact, when you do that, you get a log transform of multiplicity 2. Now if you look at a point where the sphere of self-intersection minus 4 and minus 1 meet, you can blow up again, and you get a configuration that looks like the one on the right. And in it, you see minus 5, minus 2, which is the configuration I was calling C3. You can rationally blow that down, and you get the log transform of multiplicity 3 on the end. So this tells you that you can get all log transforms on simply connected elliptic surface by the process of blowing up and then rationally blowing down. So you make things a little worse by getting bigger four manifolds, but then they get better when you rationally blow down, and you don't get the same thing back again. The torus of the log transform is back in the original picture. It's one of the tori that has degenerated to this nodal fiber. Okay, well, so using this idea, you can prove the log transform formula for Seiberg-Witten from this rational blowdown formula. In fact, that's how it originally got proved. Okay, so next I want to talk about what I think is one of the major advances in the subject. So, due to Jung-Il Park. So, here was his idea. So, in some ways, it was informed by this last construction of log transforms. So, elliptic surfaces can have lots of different kinds of singular fibers. I just mentioned the nodal fiber. Here's another one. So, this one on the right is called an E6 tilde fiber. It's really, it's a plumbing of minus 2 spheres. It's built from 7 minus 2 spheres in that configuration. And it turns out that there's an elliptic fibration on E1 which has 4 nodal fibers plus an E6 tilde fiber. And in fact, in the red, I've denoted which homology classes what spheres represent. So there's a picture of E1 with all these singular fibers, and as well, I've shown one of the sections of this elliptic fibration. So the exceptional curves, which are the lines in the various CP2 bars. Remember, E1 is CP2 connected some 9 CP2 bars. So there are 9 of these standard sections, and I've shown one of them. And that's the curve of self-intersection minus 1 there. And E1 has B plus equals 1 and B minus equals 9. And now what you want to do is blow up 4 times at the points where the nodal fibers have at their double points. And so now we have 4 pictures. So those 4 curves whose names I've labeled in red all have self-intersection minus 4, just like before. And now we have E1 blown up 4 times. So now B minus is equal to 13. But now we have, in this configuration, we can resolve the double points that lie on the section at the bottom. And if you do that, every time that you resolve the double point along with the minus 4 sphere, you'll lower the self-intersection of your curve by 2. So in the end, what you see is a curve of self-intersection minus 9. That's 2 sphere, self-intersection minus 9 along the bottom. Or I've written down what homology class it represents. And then all these, from the E6 tilde fiber, all these 2 spheres of self-intersection minus 2 that intersect it. And in red, I've shown 5 of them. Yeah? And so this is actually the configuration C7, which can be rationally blown down. Okay, so we've blown up 4 times, so we now have B minus equals 13, but we're going to blow down a configuration of length 6. So now we're going to lower B minus by 6. And what you got is the Park manifold. So this is a simply connected 4 manifold with B plus equals 1, B minus equals 7 now, and simply connected and with Seibert-Witten non-zero. So this was the first example of an exotic P2 blown up 7 times. So his idea was, you can make things worse as long as eventually they get better. This is sort of like hoping for my retirement fund. So now, let me tell you, so using this technique of Jungle Park, lots of progress was made. So first, here is the statement about the Park manifold, which, by the way, is a symplectic manifold. Andras Stipschitz and Zoltan Szabo improved, basically using the same technique, but with a more complicated rational blowdown. They improved Park's example to work for CP2 blown up 6 times. Then Ron Stern and I showed that these examples admit infinitely many smooth structures by building knot surgery into the construction. And about 2 days after I sent Andras, Zoltan, and Jung-il a preprint, they wrote back saying, well, we can do the same thing for P minus equals 5, and they did. And now one of the most gratifying results of all of this is work that Jung-il Park and many of his co-authors have done since. So for years, smooth 4 manifolds has taken from algebraic surface theory. We steal constructions, we take their ideas, and given nothing back. But Jung-il Park and his co-author showed that these topological techniques could actually be made to work in the complex category. And so they produced complex surfaces of general type for all of these. So there are complex surfaces of general type homeomorphic to CP2 blown up n times for n between 5 and 9, 5 and 8. Unfortunately, the techniques don't seem to work for B minus less than 5. Maybe even Andras Stipschitz has proved this. I'm not quite sure. So, so the deal is now we've lost this rational blowdown technique, and we're back to surgery on tori. But the problem is that if you have a four-manifold with B plus equals 1, B minus less than or equal to A, and non-trivial Seiberg-Witten invariant, there can't be a homologically essential torus of square 0 in this manifold. And so here's an idea for a proof. Because K is a non-zero coefficient in the Seiberg-Witten invariant, so choose a K that tells you the Seiberg-Witten invariant is non-zero, then this adjunction formula that I talked about before says that it has to be orthogonal to any torus of self-intersection 0. But now the hypothesis B minus less than or equal to A tells you that C1 squared is positive. So T squared is 0, K squared is positive, and so now it's an exercise in the Cauchy-Schwarz inequality to see there's a contradiction. So if we could surger, if you could find an essential torus in any four manifold with B plus equals 1, simply connected to B plus equals 1, B minus less than or equal to 8, and get a manifold with non-trivial Seiberg-Witten invariant, well, you'd be exactly in this situation. So we can't do it. So the idea is we definitely need to work with null homologous tori. And now I probably should be embarrassed by the next set of slides, but what the heck. I was encouraged to include them by the response to them when I showed them to Lawrence Roberts, so I'm blaming him. So that's my co-author, Ron Sterner, that Huber guy has. And so I'll just run through these quickly so I won't be too embarrassed. You'll have to read the captions yourself. But he's going to do surgery. Of course, that's a matter of opinion. But unfortunately, we can't tell the difference. We got my torus. That really hurt. Anyway, that's. I just thought that it was time. A little entertainment. So, so next, let me say something. So, a very important formula that one needs to use if you're going to do surgery on null homologous tori, a formula due to Morgan, Rufkin, and Zava. And so here's the idea. I'll try to just say something basic. So you have a torus of self-intersection 0. Its tubular neighborhood is T2 cross D2. And so I'm going to choose a basis for the first homology of the boundary 3 torus. Alpha, beta, gamma, where gamma is the meridional curve. And we'll define x PQR to be the result of surgery where you remove this torus, you glue it back in so that D2, the boundary of D2 is sent to P alpha plus Q beta plus R gamma. And so it's familiar to everybody who thinks about three manifolds from Dane surgery that this is what you need to know in order to determine the diffeomorphism type. And so let me now write Seiberg-Witten of KPQR for the coefficient of this class in the new Seiberg-Witten invariant. And now I've written a complicated formula which I sort of prefer not to talk about. So let need, right, here's a moral formula. So the general rule is if there's a formula in quotes, it doesn't have to be true. But it's basic, it's morally true. So it's what makes it not quite true are these sums, which we could talk about if you really want. But in this formula, notice that what this says, if you do surgery by killing the PQR curve on T3, then that's P times the surgery for killing the 1, 0, 0 curve plus Q times the invariant for killing the 0, 1, 0 curve and so on. Notice that third one, that you're killing the meridian, so you get X back again. And the other two are the results of what you could think of as S1 cross 0 surgery. So how can you use this formula? So you like to construct exotic smooth structures on CP2 blown up n times. And remember, we don't have essential tori to work with. So if you're going to do surgery on tori, you need to find a null homologous torus in this manifold. Well, in some manifold with b plus equals 1, b minus equals n, and pi 1 trivial. So a manifold which is homeomorphic to P2 blown up n times. And if you do that, and you do surgery with coefficient 0, k, 1. So this is, if the curve beta that has the coefficient of k in the framing, if it's null homologous in the complement of your torus, then it's acting like it's a longitude. And so you're doing something like 1 over k Dane surgery. And so it shouldn't be surprising that you're not changing the homology of the manifold. And in fact, so here I use tilde from morally equals to. So here the Seibert-Witten invariant is k times the result of 0 surgery plus the Seibert-Witten invariant in the original manifold. So this tells you that, if this 0 surgery had non-trivial Seibert-Witten invariant, you'd certainly get infinitely many distinct manifolds. Now they might not all be homeomorphic because we still have to check pi 1, but they'd be different manifolds with the same homology. So the question is, how do you achieve this? How can you make sure that when you do 0 surgery on this curve, you get a manifold with non-trivial Seibert-Witten invariant? So here's a sort of general setup. You've got this 4-manifold X prime, a torus T prime that's sitting in it, and so now everything's prime. So the generators of the homology on the boundary are alpha prime, beta prime, and gamma prime. And let's assume that T prime is a primitive, representing a primitive homology class. So that means it has a Poincare dual that intersects it once, and so its meridian must be trivial in the complement. So gamma prime trivial. Now let's assume that beta prime isn't. So now you want to do a surgery with respect to beta prime, say a 1-1 surgery. So that'll kill beta prime and move you to a smaller 4-manifold, which has now a new, this core torus T. T is now null homologous because it's, let me say it. When you do a 0-1-1 surgery, the meridian of T becomes identified with beta prime plus gamma prime. Well, gamma prime is trivial in the complement, and beta prime isn't. So their sum is not trivial in the complement. So that says that T can't have a dual class. So it becomes null homologous. And beta becomes 0 because in the surgery, beta is identified with gamma prime, which was the old meridian, which was trivial in the complement. And conversely, if you do a 0-1-0 surgery, in other words, a surgery that kills beta in X, then you're going to get into situation A. So what we have is that surgery on A gives B, and surgery on B gives A. And surgery on A lowers B1 by 1 because you're killing the class beta prime. And the Cyber-Witten invariant, again, satisfies this formula. If you do a 1 over K surgery with respect to beta in X, then you once again have this Cyber-Witten formula.
Where does that equation live?
Where does the equation yeah, so this equation lives in the group ring on X of 1 over K surgery, 0K1. Even though it seems to have elements from these others. Remember, what the formula really means is this is the way to compute the coefficients of variables in the Laurent polynomial on the left from the coefficients of the variables on the right. That's why I sort of said morally equal. So it tells you how to calculate, but it's not really an equality as such. Okay, so one of the key ways for making sure the Cyber-Witten invariant of a manifold is non-zero is to make sure it's symplectic. So if X prime is a symplectic 4 manifold and T prime is a Lagrangian torus in X prime, then there's a preferred framing for this torus called the Lagrangian framing. It's the framing so that all the push-offs with respect to that framing remain Lagrangian. And if you do a 1 over K surgery with respect to this framing, the result will again be symplectic. So this is a theorem of Aru, Donaldson, and Pizzarkov. And in their paper, they refer to this kind of surgery as Luttinger surgery. And so this is how we can make sure that the Cyber-Witten invariant of X prime is not zero. So, so the technique that we use to do this is, I think, appropriately called reverse engineering. So you want to construct exotic smooth structures on X prime. So step 1 is to find a manifold you can think of as a model manifold, which is symplectic, has the same Euler characteristic and signature as the manifold that you're trying to construct new smooth structures on. And this is because, you know, removing a torus and twisting it and putting it back don't change either the Euler characteristic or the signature. But now you want to assume that B1 is not zero. And so then you look around for Lagrangian tori, which are disjoint and which contain generators of H1, because you'd like to do surgery on these tori to kill these B1 classes that generate H1. And so now you perform Luttinger surgery on those tori. It kills H1, and the result is going to be a symplectic manifold with the same Euler characteristic and signature as your model, but with B1 equals 0. And the second homology, each time you do a surgery, the second homology will be reduced by a hyperbolic pair. And in fact, X will contain a useful null homologous torus because when you look at one step higher, so the manifold you surgery directly to get X, that's manifold A in the previous slide where we had A and B. So X is the manifold B. The symplectic manifold one step up is the manifold A. Because it's symplectic, because B plus is one higher than that of X, so now if we're trying to construct a manifold when B plus is 1, now the X prime will have B plus equals 2. So the fact that it's symplectic, we'll say that its Cyber-Witten invariant is non-zero. Okay, so that gives you the Cyber-Witten invariant of 0 surgery. Well, step 5 is to get lucky. Well, here's what happens. So,
I thought when you said surgery, you meant.
I mean blood transport. Yeah.
So we're so we
because the Euler characteristic and the signature don't change. So the signature doesn't change, the Euler characteristic doesn't change, but you've reduced B1 by 1. So to keep the same Euler characteristic, you have to reduce B2 by 2. And to keep the same signature, that better be a hyperbolic pair. Is that okay?
Oh, I see. So what would the potential is not preserving all of that?
No, not here, because you're doing it on null homologous tori. Well, going backwards, I just lied. I'm sorry. I don't do it on purpose. I can't help myself. Okay, yeah, so you're not preserving the homeomorphism because you're reducing Betty numbers. So if all these 1 over k surgeries on X are simply connected, well, then you're going to get an infinite family of manifolds which are all homeomorphic. So here's a place where you can use it. So maybe this will make some of this clearer. So suppose you start with the model manifold second symmetric power on the surface of genus 3. That has the same Euler characteristic and signature as CP2 blown up 3 times. And pi 1 is a nice feature of being abelian. It's H1 of sigma 3. B1 is 6. In fact, it's easy to find disjoint Lagrangian tori carrying a basis for H1. And if you do 6 Lagrangian plus 1 surgeries, so these 6 Luttinger surgeries, they give you a symplectic manifold which is simply connected, non-trivial Seidel-Witten invariant, but homeomorphic to CP2 blown up 3 times. But this symplectic manifold is not diffeomorphic to CP2 blown up 3 times. In some sense, that I'll try to make clear in a second, you should think of this as the general type manifold, which is homeomorphic to this rational surface. And this manifold has a useful null homologous torus so that you get an infinite family for 1 over k surgeries. And so these examples were first found by Baldrige and Kirk and Akhmedov and Park, but they used the same technique, but their models were constructed by cut and paste rather than by starting with a Kähler surface. So how do you find the model manifold? Well, one way is just like I did. You name a Kähler surface and hope that surgeries on it will take you to the right place. A second way is cut and paste, and in fact, Akhmedov and Park showed how to do this to construct exotic manifolds homeomorphic to CP2 blown up twice. The third way is a way I like to call Santeria surgery, because it reminds me of a rite that used to be performed often in New Orleans, where you pull out the heart of a manifold, twist it, and put it back. So you may have seen these. So you find a useful null homologous torus directly in a standard manifold and twist it to change the smooth structure. And in fact, you can do this. So Ronstein and I have shown how to do this for n between 2 and 7. So the key to finding these tori to twist has to do with the canonical class. So if you think about a rational surface, so let's think about a rational surface, CP2 blown up less than 9 times, then its canonical class is minus 3 times the line plus all the exceptional curves. So notice that this class is not, it's not represented by a complex curve because we have minus 3h plus the exceptional curves. In fact, minus k is represented by a homomorphic curve. And in fact, it's represented by a torus, as you know. And if you plug into the injunction formula, you'll see why. But, so what we're looking for instead is an exotic symplectic manifold, homeomorphic to CP2 blown up this many times, but now with the canonical class pseudo-holomorphic rather than minus the canonical class pseudo-holomorphic. And in this case, the injunction formula would tell you what the genus of such a surface would be. and it would be 10 minus n. So for example, if you could find an exotic CP2, then its canonical class would have genus 10 rather than 1. And in fact, this is true. I mean, there are these fake CP2s of Mumford and Gopal Prasad, and they've been classified by this beautiful work of Cartwright, where he showed there are exactly 50 of them. And the canonical class is genus 10. So what you want to do is look for tori so that when you do surgery, the genus of the canonical class is forced up. So let me show you how to do that. So here's a picture of CP2. So it's a picture of CP2 as a union of 3 coordinate neighborhoods. And so each of these coordinate neighborhoods is a ball. It's built from a 1 handle and a 2 handle attached with framing plus 1. And you can see that framing is right because if you want to see the generators, the homology classes that generate CP2, look at a loop that runs around the 1 handle. It slides across into the next chamber and bounds the belt disc of the 2 handle in the next chamber. But then it slides back over it's parallel to the attaching circle for the 2 handle, which bounds a disk of self-intersection plus 1. So those two put together give you your, the line in CP2. But now let's blow up 3 times. So if we blow up 3 times, we see a picture like this, where, as I pointed out, these meridians get identified. And so well, it's sort of an amalgam of a Kirby calculus diagram. It's a Kirby calculus diagram in each of the 3 pieces.
They look like diagrams of the ball.
They are. It's diagram. Each one is the diagram for a 4 ball blown up. On the right. On the left, it's a diagram for a ball.
But why is the ball then have CP2 equals to the
Because CP2 is the union of 3 coordinate neighborhoods. The neighborhoods of the 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. And that's what we see there. It's the 3 neighborhoods. And if you construct these spheres of self-intersection plus 1, the way I just told you how to, you'll see 3 spheres that intersect each other once. These are 3 standard hyperplanes in CP2. And now if you blow up each of these balls, then we see CP2 blown up 3 times. And if the meridian, so the loop that runs around the 1 handle in 1 chamber bounds a normal disk to the 2 handle in its adjacent chamber. So that means that if we beam double that loop, as over here, they bound disjoint 2 disks in the neighboring chamber. So what you can do is add those 2 disks to 1 chamber and scoop them out of the adjacent one. So you've added 2 handles on one side and subtracted 2 handles, which is the same as adding 1 handles to the other side. So here's a picture of what you see in each piece. I didn't realize it looked so big. Notice the green part, because here's what the green part is. So if you take S1 cross a solid torus, T2 cross D2, and then remove point cross a punctured torus, so the punctured torus is that blue one there. That's exactly the green part. And in there, you see a pair of beam tori. So it's S1 cross the beam double of the core loop of the solid torus. Of course, that torus, the core loop of the solid torus, isn't there anymore. But because you've removed this punctured torus. But the beam double is still there. And the canonical class for CP2 blown up 3 times intersects that picture in a pair of normal disks. So if you do surgeries on both of those tori, those normal disks don't cut through anymore. The only way they can survive is by running around the being double. So doing both those surgeries, in fact, adds genus 2 to the canonical class. Well, in the construction for CP2 blown up 3 times that I mentioned, you do 6 surgeries. Each one increases the genus of the canonical class by 1. So when you're done, you get genus 7, which is exactly the genus that's predicted by the adjunction formula. So, but in fact, 1 surgery will suffice because you can prove that if you do less than the maximal number of surgeries, you don't change the manifold at all. It remains CP2 blown up 3 times. And there's a similar construction of exotic CP2 blown up twice. And so the moral I want to end with is that we should look for useful embeddings of this manifold A, which is strictly smaller than the neighborhood of embedded torus at self-intersection 0, an essential torus at self-intersection 0. So let me conclude by telling you about the current state of affairs. I'm sorry, I haven't been over. So first of all, there are exotic smooth structures on P2 blown up n times for n between 2 and 9. For n bigger than or equal to 10, there are exotic smooth structures. You get them just by blowing up the exotic structures on smaller manifolds. But no examples are known which are minimal, meaning no 2 spheres of self-intersection -1. And you might conjecture there are none, because for these manifolds, C1 squared, or if you like, 3 times the signature plus twice the Euler characteristic, is negative. What's still open? CP2, CP2 blown up, and S2 cross S2. So now there are proposed examples for S2 cross S2, but that are currently on the web, but the pi1 calculation in that paper is incorrect. So these constructions use reverse engineering, where the model is a 2-sphere, a genus 2 bundle over genus 2. So that means it's aspherical. So here's a conjecture which would tell you that such examples could never work. But I don't know how to prove this conjecture. Is Yashi here? So the conjecture is that if you do Lagrangian or Luttinger surgery on a symplectically aspherical 4 manifold. So symplectically aspherical means that the symplectic form integrates to 0 on the image of pi2. So the conjecture is that if you do Luttinger surgery on one of these, it's again symplectically aspherical. And it's a fairly easy exercise to see that symplectically aspherical 4 manifolds have to have infinite pi1. So you should never be able to get S2 cross S2 from a genus 2 bundle or genus 2 surface. Now you have to be careful though, that when I say Luttinger surgeries, that's important, because you can do surgeries that don't preserve the symplectic form and get non-symplectically aspherical manifolds. And finally, let me conclude with a really optimistic conjecture. I'd like to conjecture that every simply connected smooth 4 manifold can be obtained by surgery on tori and connected sum of copies of S4 plus or minus CP2 and S2 cross S2. Of course, I have no way of knowing how to prove it. Thanks. I'm sorry. Oh, well, I was only talking about B plus equals 1. That's a talk I can't give. I'm sorry. Yeah, so the calculation in that paper is incorrect, but I never bothered to try to find a representation or something. Yes. Yeah, it's again a logarithmic transform with certain coefficients with respect to the Lagrangian framing on Lagrangian toroids. So if you choose the right